Okay, so just started recording for folks joining us. We're looking at problem 1, the volume under the paraboloid z equals 4 minus x squared minus y squared above the xy plane and outside x squared plus y squared equals 1. So I just started taking a look at what each one of these surfaces will look like. Z equals 4 minus x squared minus y squared. By level curves, we determined that this is a paraboloid with circular cross sections parallel to the xy plane. I've sketched that in pink. And I'm just finding some intercepts now by setting x and y equal to 0, finding that z equals 4 up here. And if we set z equal to 0, we get 0 equals 4 minus x squared minus y squared. And adding x squared and y squared to both sides, we get x squared plus y squared equals 4, which would be a circle centered at the origin of radius 2. So that's what we have. That's that pink circle here in the xy plane that has radius 2. And the top of the paraboloid is up here at z equals 4. So that's our first surface. We want the volume bounded underneath that. Above the xy plane, that's good, right? That'll be the signed volume from our integral. And then outside, x squared plus y squared equals 1. So x squared plus y squared equals 1, that's a cylinder, right? It's a unit cylinder centered at the origin. I've drawn that in blue there. And so we want, it's interesting thinking about what this region is going to be. It's almost like a Calc 1 revolution problem, or I guess maybe a Calc 1, Calc 2 revolution problem. We could have done that except for this kind of annoying piece up here on top. There's probably a good way to turn this into just a volume of revolution problem, but it's really not bad if we convert this or we think about this in the right way. So this problem, like if we observe the geometry here, if we have problems that are really nice in rectangular coordinates, like if we have cross sections that look like rectangles or squares or parallelograms, right, those are really amenable to rectangular coordinates x, y, and z. What I notice about the geometry here is that there's a radial symmetry, right? There's like a rotational symmetry, and then also that there's nice, neat cross sections as we go in the z direction. And when you have a situation like that, that suggests cylindrical coordinates, right? Because cylindrical coordinates use r and theta. And if we have that nice symmetry radially around some angle theta, then thinking of it in those terms will be helpful. The fact that it stacks nicely, it's very similar going vertically in the z direction, that also suggests that cylindrical coordinates might be a good choice for us here. So let's see. So what can we do here? Well, let's do a couple things here. Let's take a look. Let's convert our function of x and y into a function of r and theta. So we have a couple conversion factors or ways that we can do this. We do have x equals r cosine theta and y equals r sine theta. The other one that we can use here is that r squared equals x squared plus y squared. And if that's not clear, like where this one comes from, if you imagine taking x and y and squaring them, we get r squared cosine theta and r squared sine squared theta. Factor out the r squared, and we have a Pythagorean identity of sine squared plus cosine squared equals 1. So these are different ways to convert into cylindrical coordinates. There's other ones we could use as well if you ever need to like change to a theta or something like that. This one's not bad because if you look at the function that we have, f of x comma y is 4 minus x squared minus y squared, right? So if we want to write that in terms of r and theta, f of x comma y we could write as 4 minus the quantity x squared plus y squared. And so then changing it into these cylindrical coordinates is pretty easy. We'll just swap out that x squared minus y, or x squared plus y squared for an r squared. I'll just pause there for a minute. Any questions on that conversion? Okay. All right, so let's see what else we have here. So if we think about the region we're trying to integrate in the direction of z, we have this sort of, washer shape here. Right, so we're trying to integrate those. And that region's pretty easy to represent in terms of r and theta. So that inner cylinder here, x squared plus y squared equals 1, Well, in cylindrical coordinates, that's just r equals 1. So what we need then is we'd be looking at radii that are at least 1 and that are at most 2, right? Those would be our endpoints of integration in terms of r. We got the upper endpoint of integration by finding where our surface intersected the xy plane, right? We got x squared plus y squared equals 4, and again, in cylindrical coordinates, that would be r equals 2. And then the cylinder boundary here is x squared plus y squared equals 1, so our minimum value of r would be 1. So we're thinking about setting up a double integral in terms of r and theta. R would vary between 1 and 2. Those would be our endpoints of integration. Thinking about theta to have a full revolution here, theta would need to sweep through 2 pi radians to get all of our region here. So I think we're ready to set up our integral here. The volume of the region that we're talking about here would be a double integral. I'm going to take our function z, but written in terms of r and theta. Okay, so we have 4. I'm going to come back for my endpoints of integration. I'll give us a little bit of room there. So we have 4 minus r squared. Right, that's our expression for z. And now, as a reminder, our area differential, you guys are probably used to doing a bunch of problems where we have dx, dy, dy, dx, things like that. When we're integrating using polar, or I guess the cylindrical coordinates here, our dA is given by r dr d theta. Okay, that's really important that it's not just dr d theta. If you look in the books or on Khan Academy, I think there's a nice little video about where this comes from, why it's r dr d theta instead of just dr d theta. So it comes from basically looking at the subtraction of 2 pieces of pizza, basically a sector minus a sector. I think we talked about that before break, but anyway, make sure you get that r there. And then our endpoints of integration, in terms of r, as we just mentioned, we're going to go from r equals 1 to r equals 2. And for theta, we're going to go from theta equals 0 to theta equals 2 pi, right? And so looking at this, this won't be a bad integral to evaluate. I'm just going to copy it over here, having distributed that r to these 2 terms. So 4r minus r cubed, all dr d theta. Okay, so not a bad integral. So integrate in terms of r. We have 2r squared. Let's see. Whoops. Minus 1/4 r to the 4th. Evaluated at 2 and 1. Okay, so if we evaluate this at 2 and 1, we will get, let's see, so that'd be 2 times 2 squared is 4, sorry, 2 times 2 squared is 8, minus 1/4. So there's evaluated at 2. Then we subtract off 2 minus 1/4. Okay, let's see what we get here. So that's 8 minus 4 is 4. Minus 2 is 2. Plus 1/4, so 2 1/4 is what I'm getting here. Okay, so 2 1/4, that would be 9/4. And let me just make sure we did that right. So let's see. 2 squared is 4, times 2 is 8, minus 1/4 is 16, minus the quantity 2 minus 1/4. Okay, so that looks good. 8 minus 4 minus 2, minus negative 1/4. Right, and so almost done here. This is going to be easy. Lower endpoint would be 0. So we have 9/4 theta evaluated at 2 pi 0, which would just be 18 pi over 4, or reduced 9 pi over 2. So I'm looking at the key here that was posted. I think there's an error in the key. I just see a mistake in the integration step. I think, yeah. So if you're looking at the key, there's probably a different answer here. I'll get this confirmed and make sure that we have the correct answer. I just want to pause here and see if there's any questions about process. Hopefully I stayed on the whiteboard. I mostly did. Any questions so far?
All made sense to me.
Say that again?
No question.
Nice. All right. All right, so give me a sec. I will erase this and we'll head on to the next problem. Okay, problem 2, find the mapping that maps the unit disk u squared plus v squared is less than or equal to 1 onto the interior of the ellipse x over a squared plus y over b squared is less than or equal to 1. Then use the change of variables formula to prove the area of an ellipse is pi a b. Okay, all right, so well, first we have to believe that there is a mapping from the unit disk to the interior of the ellipse. If we think about the interior of that ellipse, that's the inside of an ellipse. And you don't need to know a whole lot about the geometry of the ellipse here, but a and b are the parameters that control the scale in the x and the y direction, respectively. But it would make sense that we can turn a circle into an ellipse by sort of stretching or compressing it, right? If we just took all the points on the circle and or the unit disk, we multiplied them by a, right? A is that scale factor horizontally. We took all the y coordinates and we multiplied them by b, that would transform our circle into an ellipse. So here's how we can do that. Here's our definition or our mapping. I'm going to use F. There's no reason to use that or any other letter, but here's the relationship between x and u and y and v that I just described. So if we say x equals a times u and y equals b times v, if it's a little bit tricky to see where those came from, here are our original equations. So we have u squared plus v squared is less than or equal to 1. And then we have this ellipse x over a squared plus y over b squared is less than or equal to 1. And what we can see is that these are like very much in the same form if we let u equal x over a and if we let v equal y over b. So this mapping here, x equals a over u, that's the same as saying like u equals x over a and v equals y over b, right? So that very clearly shows where these two things came from. Okay, so then our equation u squared plus v squared is less than or equal to 1 will be equivalent to this inequality here, right? That gives us the interior of the ellipse if we stick to this mapping here. So what we want to do then to find the volume here, or sorry, to find the area, we're going to do a double integral here. And here's the notation I'm going to use. Let's let d equal the area of the ellipse. The ellipse. And also d sub 0 or d sub circle. That'll be the area of the circle. Right, so we're gonna find a relationship between these two things. So then the area of our ellipse can be written as a double integral over the region D of just dx dy, right? That's like just a way of saying, all right, the area of the ellipse is the area of the ellipse. But what we can do now is, using our change of variables, write it in terms of not x and y, but u and v. So u and v defined the area of the circle. So now we'd be integrating a region bounded not by an ellipse, but by a circle. And then we'd have to use our change of base formula. And so what that would be is our partial, del x comma y over del u comma v du dv, right? And so now this quantity here will come from our Jacobian determinant here. So I'll do that calculation over here. So we'll call that. All right, so if we're calling this mapping here just capital F, just for notation's sake, we'll take the Jacobian based on that relationship for our quantity here. Okay, so here's the determinant that we want. We want del x del u, and then we have del x del v, del y del u, and del y del v. Okay, so that's what's going to go into our new change of variable double integral. Okay, so let's figure out what these things are. Partial x with respect to u. We'll go up here. There's x. X equals a times u. So when we take a partial derivative with respect to u, we'll just get a. And then x equals au. So if we take a partial with respect to v, the derivative will just be 0. Likewise, taking a look at our expression for u is b times v, and so our partial with respect to u is 0, and our partial with respect to v is just b. And so then the value of this determinant is just a, b. Okay, so let's see, we're going to use that in place right here. And so then our area equation, I'm running out of space here. I think I'm going to write one more line up here. So double integral. It's over not the ellipse, but over the circle. And that's good news because we know how to find the area of a circle, right? That's something that we can evaluate pretty easily. And we've determined that the Jacobian is AB. 1 times AB is AB, right? du dv. And so what this integral represents is just over a region d sub 0, which we don't really need an integral to evaluate. We know the area of that region, right? That's just the unit circle times AB. And like that's pretty much it right there. That's like the end of the problem, because right, this double integral is just going to give us a circle of radius 1. And so a circle of radius 1 has area pi. And so we have pi times A times B. And pi times A times B was set up originally as the area of our ellipse. So just to recap, I wanted to find the area of an ellipse. We did a change of variables between our circle and our ellipse. In doing so, we found a relationship between an integral, a double integral giving the area of the ellipse, and a simpler double integral over the area of a circle. To do that change of base, we calculated the Jacobian here using partial derivatives, and it gave us this nice result that is also the formula for area of an ellipse. Any questions about that one? Awesome. Well, thank you, folks, for tuning in. I will pause the recording now, I guess.